Okay, so the web work, the online problems, I just posted here in readings and homework, the very first post. So after this post here for today's take-home quiz, so now the next post is everything you need to know to get going. So where to go? So this should say 270, not 271. Okay, but this is all important information. There's not much to read, but that's the very most important information. So read that all carefully. What we'll do with this is it will mostly be extra credit, but some of it may be required. Okay, some of it may be required, and I will, when I put today's the homework post, say for Tuesday the 18th. Is that right? 5 days away. Yeah, for Tuesday the 18th, when I put that next homework post up, it will explain if there's any of that that's actually required. But then it's the first 3 sets are due next Thursday night. Okay, so then anything that's required that you can get going on this weekend, that for credit, that will close next Thursday night, so you have actually a whole week. Okay? Okay, so just here's the information about web work itself. When I put Tuesday's homework post, read that carefully in terms of you may have written and some of this online extra credit. Actually, some of those might be required, okay, as part of your normal homework grade. Most of it, though, for the rest of the semester, it will be extra credit. And all really good practice for the third exam and for the final exam, okay? So it's actually all stuff we've normally assigned. All these web works we've normally assigned as normal homework in previous semesters. So this semester it's going to be extra credit. So highly, highly encouraged and recommended, okay, to prepare for the exams. Any questions on that? Okay, let's jump right in here. We can now. Okay. Okay, let's work on this. So this is applying what we were talking about last time. So if you knew things about the first derivative and the second derivative, could you make conclusions about the original function? So this is the idea of coordinating information about the function and the 2 derivatives to sketch or understand the behavior of the original accumulation function. Okay, so for instance, at x equals 0, how would I know what the value of the function is at x equals 0? How would I know? Yeah, so g of 0, right? G of 0. How do I know what the value of the first derivative is at x equals 0? What would I need to do? G prime of 0. How do I get that? Yeah, so you're going to find, we've got the rules now. We've got the shortcut rules. Okay, this is super easy derivative, right? So we're going to find the derivative of that, and then we're going to evaluate it at 0. Same with the second derivative. Okay, so when we do that, we're gonna skip all that. Okay, so does that make sense? That you would find the first derivative using your mastery rules. That would be the rate of change function for g. And then you're going to take the derivative of that. And that would be the second derivative. And that tells us information about how the rate of change is changing, right? How the rate of change changes. We've been working on that for the last week. Also tells us how that accumulation function turns, right? How does it turn? Does it turn down or does it turn up? Okay, so when you do all that stuff, so there's the first derivative, there's the second derivative. We're going to evaluate these values, and here's what we get. Now let me just take a look at this first one. So I've got the first derivative of -8. So this is at x equals 0. So at the moment x equals 0, the first derivative is -8, and the second derivative is positive 24. What different things can we conclude now about g? What can we conclude about g if the first derivative is -8 and the second derivative is 24? So just tell me one thing we can conclude. Where's Christina Smith? Christina. All right. What's turning up? What's that? The original function g? Because how'd you know that? What's positive? So here's the thing with this. When you're having conversations about these, it is a new 4-letter word. It. You thought it was 2 letters. Now it's a 4-letter word. Why? Because when you say there's actually, we're talking about 3 different functions. So you say, it's increasing. It's turning down. It's, so what do you mean by it? So don't use the word it. Always describe exactly what function or quantity or value you're talking about. Okay? So she says, because it's positive. By it, you meant? What's that? Not sure. Okay, so she said it was turning up. Do you agree with that? What's it? What's turning up? G, the original function, is turning up because, right, because our second derivative is positive. What does that tell us about the first derivative? The fact that the second derivative is positive tells us what about the first derivative? The first derivative is increasing. Agree? Yeah. If a rate of change or derivative is positive, that tells us the original function is increasing. So this tells us, this positive tells us this one's increasing. And what does this -8 tell us? That g is decreasing. So what do we have? G is decreasing and turning up. Well, how will the graph of g look like in the moment x equals 0 if it's decreasing and turning up? Draw it with your finger in the air. So in the vicinity, you should be thinking this of x equals 0. At the moment x equals 0, you should be thinking like this. Decreasing but turning up. Decreasing but turning up. Okay, quickly, see if you can do the same thing. So this is what? Graph of g now. Graph of g. At x. So we're going to do that for 1, 2, 3, 4 more. Do this for the rest of the x values. So at x equals 0, decreasing but turning up. In that moment, x equals 0. Do the others, quick. See how fast you can do them. Work together. We got a lot to do today, so I'm going to be moving fast. All right, let's see how you did. Where's Anna Stimson? Anna here? How did this first one go? So what does zero, the first derivative of zero, tell us? The rate of change is negative, but the rate of change is zero. Sorry. Yeah, so what does a zero first derivative equal to zero? Pause, right? So if it's just constant for a moment, remember we called that a pause, right? A pause. Yeah, constant for a moment, and then what does the second derivative tell us? Good. And what will that mean for g then? Okay, so yeah, so this is good. You said that the first derivative is increasing, but at the pause though, even though the first derivative is increasing, that means that the function is doing what? The function is turning up. So we've got a pause when the function is turning up. And essentially then what do we have? If we have a pause while it's turning up. So where along there is it pausing? Where along there is the accumulation pausing? Is it pausing now? Where's the pause? There, at the bottom. So essentially this is, what do we call this? This is our local minimum we worked on last time, right? If it's turning up, and there's a moment where it pauses, that's going to be the very bottom, where that accumulation is staying constant for a moment. So this is our local min. At x equals 0.5. At x equals 0.5, we have a local min because we know it's turning up, but while it's turning up, there's a pause. That's got to be at the low point where that value of g is staying constant. Yeah.
I was just looking and I saw that you had accidentally switched put 1.5 above 1 and 3 above 2 in your x equals column.
Okay.
I just noticed that they were out of order.
Yeah, it doesn't matter. We're just identifying all these individually.
Oh, okay.
Yeah, we're just identifying each one individually for each x value, so that's not doesn't have a consequence on this activity.
Oh,
okay. Okay. Other questions on at x equals 0.5? Yeah.
Why is it not the
There was local max and the rest stops.
Yes, the rest stops. Why isn't that?
Because it's in the rest stop. Remember what was our second derivative in the rest stop? It also paused. So in the rest stops, both the accumulation and the rate of change paused. So both of those derivatives are zero in a rest stop. So but when the second derivative is positive, that means that the first derivative is not pausing but increasing. So this is how it looks when the rate of change increases, right? The rate of change becomes less negative or more positive. If you also know that the function, the accumulation is pausing, that's at that moment at the lowest point. Okay, what about this? Function is increasing or decreasing? Increasing, and the function is g turning down. Increasing, turning down. Draw it with your finger. Should look like this. At 1.5. At 1.5, we have this increasing because the first derivative is positive, and the accumulation is turning down because the second derivative is negative. Okay, what about this? What does this tell us? That the function is increasing. And what does this tell us? That the rate of change is staying constant or pausing. All right, so what will that look like? It's one of two possibilities. So it's an inflection point, but not a rest stop. A rest stop is where you have both first and second derivative are zero. So it's increasing and it's not turning, right? So the rate of change is pausing. So the function is not turning. So that's what we call an inflection point. So it could look like this, or that might look like this. So either right there, so that G is increasing, right? These are not rest stops. What are rest stops? Rest stops are where the first derivative is 0 and the second derivative is 0. So it flattens out. But we know that it's still increasing. It's still increasing as the derivative pauses, or as the rate of change pauses. So here, the rate of change is increasing. Rate of change pauses and starts to decrease. Here, the rate of change is decreasing. Then the rate of change pauses and starts to increase again. So just that is not enough information to know whether you have this type, this situation, or this situation. Both of these are possible for x equals 1. Any questions on that? Yeah.
Wouldn't it mean just at that moment that we just have a straight line in our accumulation?
Right, but all these are right at that moment you have a straight line. But around, so in other places it's not straight. So yeah, exactly. So yeah, so rate of change is increasing, and then rate of change is constant, like a line, and then rate of change decreases, or other way around. You're exactly right, but it's just in the moment. Yeah. Okay, next one. Rate of change positive, second derivative positive. Draw it with your finger. That's the easiest one. Function g is increasing, rate of change is increasing, so that function is turning up, and we look like this. Okay, so our 0 and 0, that could be rest stop, but it could be other things too. Rest stop 1 or 2 from last time. But there's also situations of local max and local min where both derivatives are 0. Okay, so when you get them both 0 and that's the only information you know, the jury is out. There's lots of possibilities to that. Okay, but the ones we talked about last time, the most important ones, when both derivatives are 0, were those rest stops. Rest stops numbers 1 and 2. For instance, like this. Okay, so those were our rest stops. Those would be possibilities for that, where actually both derivatives are 0. Right there and right there. Okay, questions on this little exercise here? Okay. So we said that critical values were, last time we said critical values are where the first derivative equals 0, but then we also said it's where the first derivative does not exist. We haven't talked about that yet. Okay, so let's just quickly talk about the main situations, or the most common situations where the first derivative does not exist. Okay? So what are situations where the function value exists, but the first derivative does not exist? These would also be critical values, not only in addition to any first where the first derivative equals 0. So the first is a corner point. And the second is if the graph of the function turns vertical. Okay, why is a corner point? Why is the rate of change not defined? Is the rate of change 0 there? No, so it's coming along. We've got this constant rate of change. And then when we get to this, it looks like x equals -1, abruptly the rate changes to some negative value. So it's positive, and then all of a sudden the rate of change changes to this negative value. So right there at the corner point, what's the rate? Who knows? It doesn't exist. It doesn't exist because the rate of change changes in an instant, right? It changes in an instant, and so there is no rate of change there. Likewise, what is the rate of change here for a change in x? What's the change in y right there? No, what's the change in y for a change in x right there? It's like infinite. It's like an infinite amount of change in y for a change in x. If you make the change in x, if you keep making it smaller and smaller around that point, then that rate of change that limit will be infinity. You'll just get that dy over dx will just get extremely big. Okay, extremely big. So dy dx so that's also why another situation where the first derivative does not exist. So these are considered critical points as well. Okay, so these are critical values. So at -1 and 1, those would be considered critical values, as well as the places where the first derivative is 0. Okay, questions on that? All right, so let's do another type of example of this. So here's a function, j, 2 minus 15x plus 9x squared minus x cubed. And I want to find the critical values. So now I'm starting with a function, and I want to find the critical values. In the last example, I gave you a bunch of x values, and we could see what they were from the table. But now we want to find them. So what is it that gives us a critical value? What is it that gives us a critical value? Where's Suprit? Suprit, yes sir. How do we get what is a critical value? When what happens? First derivative? Okay. Okay, good. Right, so critical values are going to be values of x for which j prime of x equals 0. Right, and also j prime of x is not defined. We just talked about it in the last screen. So are there any x values that are going to give us the first derivative undefined in a polynomial like that? No, how do we get values that are undefined? Yes, fractions. We're x values that make a denominator 0, right? So if you get a fraction and you get an x value, you're looking for x values that make a denominator 0. That would be places of undefined. Everyone paying attention? Are we policing today? Okay. All right, so, but we're not expecting that here. We've got a polynomial that's defined for all x values. Okay, so instead we're going to look for 0. So we want to know, where does j prime equal 0? So j prime of x, we want values of x that make that 0. And so what is that? So we got negative 3x squared plus 18x minus 15 equal to 0. And I need to find values of x that make this true now. And those values of x will make the derivative 0, and it'll be critical values. So to simplify this, I could divide by negative 3, make things easier on myself. And what do I get? X squared minus 6x plus 5. And that should be real easy, right? That's totally rigged. X what? Minus 5 minus 1. Therefore, critical values are at 1 and 5. So all I know is that I have the derivative of j is 0 at 1 and at 0 at 5. But I don't, what's happening at x equals 1? I want more information. What can I do? I want to get more information about what's happening at x equals 1. So what could I do? Second derivative, right? So if I take the second derivative, I'll do that up here. Second derivative is, so we love these, right? These are, so minus 6x, what? Plus 18. Okay, so second derivative is minus 6x plus 18, and I want to know what's happening at x equals 1. So what do? Plug in 1. I want the second derivative. I want to know what's going on at 1. So I get minus 6 plus 18, or 12. All right, so I got my second derivative is 12, and my first derivative is 0 at x equals 1. What do I got at x equals 1 then? Pause, but the rate is increasing. So how could the rate be increasing and the function be pausing? What kind of thing is that? I heard inflection point and I heard local min. So the function itself is pausing because the rate is 0, And the rate is increasing the whole time through there. The rate is increasing, or the function's turning up. So what is that? That's a local min, right? So at x equals 1, I've got a pause, but while the function's turning up, while it's pausing and turning up at the same time, that's a local min at x equals 1. Okay, what about at 5? So I take the second derivative at 5. I'll do that up here. Second derivative at 5 is negative 30 plus 18 is 12. Sorry, negative 12. So talk through with the person next to you. What is happening to the function j at 5? And not just a final conclusion, but an analysis, right? A reasoning. Analysis and reasoning as to what is happening to j, or around at x equals 5, the function j. Go. All right, what about Keenan? Albert, is Keenan here? Yes, sir. What you guys talk about? What you talk about? So what do I got? I got x equals 5. I got the second derivative is negative 12. Turning down. What's it? What's turning down? Function j is turning down. Good. What else? Constant, not constant rate of change. First derivative 0. So put that all together. What would that be? Yeah, you drew it. So he drew this with his finger. This is right. And at x equals 5, my first derivative is 0, and my second derivative is negative, turning down. So j is turning down. Could it be anywhere along there? Local max, right? So it's only at the max that I get that first derivative to be 0, with j staying constant. And also, second derivative negative, meaning we're turning down like that. So local max. Questions on that? All right. Now notice, what about this? Let's look at the second derivative now. Second derivative, what would be of interest there? I got negative 6x plus 18. If we were to set that equal to 0, that would give us x equals 3. And we could take that and put it back in the first derivative to see what j prime of 3 was. Is it going to be 0? Nope. It's going to be negative 15 plus 54 minus 27, which is 12. Check my math. 42, I think it's 12, positive 12. So my second derivative is 0. My first derivative is 12. What can I conclude about j? Is it a rest stop? Not a rest stop, because the function j is doing what? Increasing, right? We got a positive first derivative, so the function's increasing, but the second derivative is 0, so the rate is pausing. The rate is pausing, and the function is heading up. And again, that could be one of two things. That could be like this, or it could be like this. So which one is it? So which one is it? Is we can kind of start piecing this function together. We know x equals 1, we have a local min. X equals 5, we have a local max. And x equals 3 is right in between them, right? So this is x equals 1, x equals 5, x equals 3 is right between them. So it has to be, what, exhibit A or exhibit B? Exhibit A. It has to be this one, right? Because it's going to come up like this, and then it's going to straighten out for a moment, and then it's going to start turning down. So here we are, like in the vicinity. So it's like we're using the numbers and making our conclusions about turning and increasing and decreasing to kind of put the graph of J together. Now, how can we get actual y values? So we know this is x equals, we know this is 1, 3, and 5. But where does J live in terms of actual y values? How can we get that? So this could be below the x-axis, this could be crossing the x-axis, this could be way up high above the x-axis. So we've only been talking about the second and first derivatives. How can we get some kind of reference to lock this thing down? What do we do? Yeah, so yeah, just get the values of J, do J of 1, J of 3, and find them, well, how much, what our accumulation is, or amount, or whatever this J function is, at those values, and then that's going to lock it down vertically. And then we have the overall shape. Questions on this example? Does it make sense? Okay, so notice that we're talking about local max and min, and these critical values, sometimes these critical values give us local maxes and mins. And so if this is some accumulation or some quantity, those are points of interest. Because if this is profit, right? If this is profit, what do we want? Do we want x equals 1, or do we want x equals 5 if this is profit? Whatever x is. Do we want to set x equal to 5 or x equal to 1 if we're talking about a profit amount function? 5, right? And if this is cost, if this is a cost function, do we want to, whatever x is, do we want to set x equal to 1, 3, or 5? 1, okay? Because we want the lowest cost possible. So this is the idea of optimization. And so with derivatives, we can look at accumulation and amount functions and pinpoint these locations of the highest and the lowest. So this is very useful and with real-world situations. Okay, so here we got this function f. And we know that with a function, various values of an independent quantity can be chosen, resulting in a corresponding value of the dependent, right? Correspondence points. That curve is just a bunch of correspondence points of x values and their corresponding values of the dependent variable, which we can represent with function notation, f of x1, f of x2, etc. So the big question with optimization is, we want to find the best value of the dependent variable, quote unquote best, right? We want the best value of the dependent. And so then the question is, like I just asked you, what value of the independent variable should we choose in order to get the best value of the dependent? That's the idea of optimization. So we've got this key independent variable. It could be time. It could be number of units sold and produced. It could be lots of things, okay? How are we going to choose? And we've got freedom, right? We've got freedom to choose the independent variable as we wish. How should we choose it to get the best resulting value of the dependent variable? That's the idea of optimization. Okay? So first of all, we'll have to know this function f. Okay? And so when we do these problems, the whole problem will revolve around this function f, creating it and then analyzing it. Okay? It might not be called f, but whatever we call it, okay? We also have to know what do we mean by the best? Do we mean by is that the maximum or the minimum? What is the best in our given situation? And then we have to figure out what interval or intervals of the independent variable are relevant or make sense. Okay, we're going to call that the applicable domain, right? So in real-world situations, so maybe in this real-world situation, X greater than 55 is not relevant. It's just not relevant, or 35. It's not relevant in the situation. Maybe only from 6 to 25 would be applicable values of X. So we need to know that as well. So let's talk about that much of it. So what independent variable value would result in the maximum value of the dependent variable if the applicable domain was from 0? So so if I'm going from 0 to 30, I don't care about this. This doesn't, whatever my values of X are, greater than 30 doesn't make sense. It wouldn't make sense for X to be greater than 30. It only makes sense in the real world for X to be between 0 and 30, and I want the maximum value of my function. How am I going to choose X to get the maximum value? Tell the person next to you. How am I going to choose X to get the maximum value? Okay, ZU. Lou, where's ZU? Is he here? ZU. How am I going to choose X to get the maximum value of F? How should I choose X? Not sure. Okay. How about Evan Johnson? Is Evan here? Nope. No Evan. Okay. How about Mark Bresser? Not here. How about Ashley Roman? No. What value? I just looking at this picture. What? Just tell me the X value you want to pick to get the maximum value of that. What X do you want to pick? She wants 5. Agree with that? Yeah. Right. So where's the highest value of F I can get? No, it's this Y value, right? When I say the highest value, it's this Y value right here because it's this correspondence point. And so something around 5, somewhere around here, around 5 is going to give me the highest value of F. Make sense? See that? Okay. Next one. What about if the applicable domain is from 10 to 35? So now what makes sense for X is only from 10 to 35. And I want the maximum value. Oh yeah, so and then what did you say before you said 5? What made it, why did you choose 5? You said it before. The local max, right? So, and that the reason that she chose around 5 was because there was a local max there, right? There's a local max there. Okay, now, what about the applicable domain is from 10 to 35 only? X values less than 10 don't make sense in our given situation. X values greater than 35 don't make sense in our given situation. Go. How would you pick X to get the highest value of F? Go. What do you think? Where's Jedediah? What do you think? What X value you want to pick? He wants to pick 10. Agree? Is it a local max like last time? Is that a local max? Yeah, right. So there is a local max in that interval here, but the starting value, although not a local max, is a higher value of F than the local max in that interval. Do you see it? Key point, right? So in the first case, it was the local max in the interval that got us the highest value of F. Now this time, it wasn't the local max, but what? The starting point of the interval. Okay, another example. 14 to 24. 14 to 24. And I want the highest value. What do you Local max? What do you think? So what x value? If the only x values we're considering are from 14 to 24. I'm going to pick x equals what? You should be thinking 24. 24 gives me the highest value of f. Again, is it a local max at 24? Not quite, actually. So, yeah, it's not quite the local max. But what is it? It's what now the last point of the interval. It's the final point of the interval. Almost a local max, not quite. Same thing with minimums. So here's minimum from 0 to 30. From 0 to 30. I want the lowest value of f for all those x values from 0 to 30. What should I pick? 30. Is it local minimum? No, but what is it? It's at the end point, right? It's the end point. 7 to 27. Uh-oh, my yawner's back. 7 to 27. What value of x will I pick to get the lowest value of f? If the only values of x that make sense in our situation are 7 to 27. Where's Nicholas Patterson? Nicholas, tell me. And why 16? Because? Yeah. So in this case, for that particular domain, if we want the lowest, we're going to use the local min. That's the lowest value that f attains in that interval from 7 to 27. So the largest and the smallest are always occurring at certain places. Where are those places that they're always occurring? So these values, we said, we want the best value of f. Which value of the independent variable should we choose? We don't want to try every single one because in a given interval, there's an infinite number of x values. It would take forever to try them all. So instead, we want to narrow it down. We know that they're always occurring where? Yeah. All right, so either at the endpoints, we saw lots of them occur at the endpoints, or at a local max or local min, critical points. Good, so we can make our life a whole lot easier if we just make a short list of all the possibilities. A short list of all the possibilities would be all the critical points that are within the applicable domain, and then the two endpoints. And then what are we going to do? We got all these x values of critical values and starting and ending values of the domain, and we want to either get the largest value of f or the smallest value of f. So what could we do? Got my list of possibilities. Yeah.
Can you then take the second order derivative and see if it's positive, then it's a minimum?
Okay, so we could do that, but then even if we find that some are minimums or maximums, then we still it could be eclipsed by starting or ending point. That's not a local maximum.
Plug them into the original function and check the value.
Yeah, just get all our list of possibilities and plug them into f. Then we'll get a list of values of the dependent variable, and then if we want the max, we just look for the biggest value. If we want the min, we look for the smallest value of all these x values. But this whole process is all about this function. And this is the centerpiece of all these problems, is this function. You have to create the function, and then what? You're going to use it. You're going to find the critical values. Or part of creating that function is finding the applicable domain, the interval that applies. Then we're going to find the critical values in that domain, and this is all about using that function. So we're going to create the function and use it to get our list of possibilities and figure out which is the best, right? The best dependent variable, whether that's max or min. But here's the key. This function, its dependent variable is the quantity that we want to maximize or minimize. The dependent variable of this function The y value is what we're trying to maximize or minimize, right? And that, I'm going to keep reminding you of that because that gives you some grounding when you start these problems. Normally in these problems, the first thing you have to do is create the function. Well, there's all these parameters and variables and the big situation flying around. So what grounds us? The function that I'm trying to write, its dependent variable is the quantity that I want to maximize or minimize. Okay, example. What two non-negative numbers, a and b, whose sum is 25, maximize the value of 2a squared plus b squared, or minimize? Okay, so what is the centerpiece of this problem? What's it all going to revolve around? A function whose dependent variable is the quantity to be maximized or minimized. A function whose dependent variable all right, so we read that question and say, what is the quantity I'm trying to maximize or minimize? What quantity is it that I'm trying to maximize or minimize? Where's Ariana? Is Ariana here? Arona? Yeah. And what, so, but now in this particular situation, what is that? What quantity is it that I'm trying to maximize or minimize? For this situation now. What am I trying to maximize or minimize, though? What am I trying to maximize or minimize? Where's Kylie? Collins, Kylie. Yeah. Trying to maximize or minimize A or B? Agree with that? What's your name right next to her? Yeah, orange shirt. Do you agree with that? Trying to maximize A or B? Is that the quantity we want to maximize or minimize? Yeah. Yeah, so it says whose sum, and we want to maximize the value of 2a squared plus b squared. So the dependent, I'm going to write a function, and the dependent variable of the function has to equal 2a squared plus b squared, because that's what I want to do. I want to maximize the value of that, 2a squared plus b squared. Okay, so I could write, say, I need f of something, right? F of something equals 2a squared plus b squared. Well, what's the problem right now that we're facing? Two variables, a and b, are both varying together, right? So I need to eliminate, I need to get this as either f of a or f of b. How am I going to do that? So this is going to be our centerpiece, right? Centerpiece is the function whose dependent variable is what we're trying to maximize or minimize, 2a squared plus b squared. But I need to write that. I can't have two variables. I just have to have one. What can I do? Yeah, so we have more information about A and B, right? They're in a relationship. A and B, their sum is 25. So from that, I've got that A plus B is 25. And this allows me, this little fact allows me to get this function that I need, right? So let's say, we'll say B equals then what? 25 minus A. And so if B equals 25 minus A, then I can put it right here for B. This is B and 25 minus A have the same value. And there's B, so I could do 2a squared plus 25 minus a squared. And now I have a function of a. So what's the key, or what was more important? This right here in the box, or this little fact, a plus b equals 25? Both are important. Both are needed. All right. But what's really our focus? Sometimes I see students doing these problems, and they're just treating all the equations the same in their mind. Everything has equal importance, or everything has equal predominance, right? There is nothing that's predominant. What is predominant? What should be? The function. The function whose dependent variable is the thing we're trying to maximize or minimize. This little fact here is the key to getting that function in one variable. But see, it's all about the function. It goes back to being about the function. We almost had it, but it was in two variables. So this little fact, a plus b equals 25, then allowed us to finish writing the function. Now, what we're also going to see is there's a little bit more to this, especially in the real world situations, okay, where you have like actual quantities like volume, temperature, mass, weight, things like that. We're also going to need the applicable domain. Okay, applicable domain are values of a that make sense, values of a that are valid in the function. What are valid values of a in this function? 0 to 25. Okay, look, it says two non-negative numbers. So that means a has to be, first of all, greater than or equal to 0 if it's non-negative. But then can it be greater than 25? Then what happens? If it's greater than 25, then what happens to b? Then b is negative. So if a and b both have to be 0, then a has to be, can be as low as 0 and as high as 25. That's when b equals 0. So this is b equals 25. When a is 0, and a equals 0, or sorry, b equals 0 when a is 25. So there's our applicable domain. It's also a very important part of the function. Okay, so we got it. We got our function whose dependent variable is the thing we're trying to maximize or minimize, and we have the applicable domain. A has to be from 0 to 25. Good so far? And what do we need to do? We need to figure out, we want to get the maximum value of f. And we saw that that can come from one of two places. We want to check what? Endpoints of the domain and critical values. Well, endpoints we already have, right? A equals 0 and 25. How do we quote-unquote check them? What do? Find out what value of 2a squared plus b squared they're going to give us, or just plug them into the function. How do we find the critical values? I'm going to take the derivative, right? I'm going to take the derivative. So this will be to get the endpoints, so our list of possibilities. So far we've got a equals 0 and 25. And now we're going to look for critical values. So to get critical values, we want the first derivative to equal 0. First derivative, 4a plus, chain rule, 2 times 25 minus a to the, am I done? Times -1. I need to solve that for a, right? That should be easy. Should be. 4a plus 50. Actually, minus 50 and plus 2a. Equals 0. So I get 6a equals 50. A equals 50 over 6. Or 25 over 3. Did I do the math right? 4a minus 50 plus 2a, that's right, so 6a equals 50. Yeah. This minus is going to distribute to both of these, to plus 50 and to the minus 2a. Are we good? So we got to ask, is 25 thirds inside the applicable domain? If it's not in the interval, then we don't even have to consider it. It's not one of our list of possibilities. Do we consider it or not? Yes, that is between 0 and 25. So there's our list of possibilities. Endpoints, and we got one critical value. So we don't even care if it's a local max or min. We just know that it's a possibility. We could figure out if it's a local max or min, but for our purposes, we don't need to, because we're just going to now check f of 0, f of 25, and f of 25 thirds, and see what we know that it has to be. The max and the min have to be from the function values from that list. All right, so here we go. F of 0 is, it's like 25 squared, 625. F of 25 is 2 times 25 squared. And f of 25 thirds is something I can't do in my head. So you could use GC or whatever. So we're gonna plug that in. 2 times 25 thirds squared plus, what is that? That's 50 thirds plus
416.667.
okay, and this is actually what, 2/3 of 25 squared. Tell me what it was again.
416.667.
Did someone else get that? Just to make sure. Do I have confirmation on that? Yeah, good. All right, so this is 625, and this is 12,050 or 1250. Okay, so what value of A gives me the maximum of that quantity 2A squared plus B squared? 25 at the end, right? The biggest is 1250. I got 625 from 0, 1250 from 25, and 416 from 25 thirds. So if I want the maximum value of 2A squared plus B squared, I'm going to choose A to be 25 and B to be 0. That's going to give me the biggest. If I want the lowest value of 2A squared plus B squared, I'm going to choose A to be 25 thirds. And then B will be, what, 25, 2/3 of 25, right? A third of 25 plus 2/3 of 25 will give me 25. So A will be 25 thirds, and B will be 2/3 of 25. So the 1/3 of 25. And I should write that out. I ran out of room, but I should write that out clearly, like with a sentence. The maximum value of 2A squared plus B squared is 1250 when A is 25 and B is 0. That's my conclusion. Write that out. Put a box around it. Questions on this example? Okay, so this is a good kind of warm up for the situation, but what we normally see though is like real world situations. Okay, so this is a nice warm up problem, but what we really see is applications and word problems. So before we do an example, I want to kind of give you some encouragement and a frame of mind to think about applying or approaching word problems. And the first thing is, we talked about this before earlier in the course, we want to orient yourself to the problem first. Don't just look for a mimic, a similar example to mimic, okay? Pretend you're coming to something you've never seen before and you just want to understand the whole situation. Okay, so my suggestion to do that is this. First, ask yourself, what is going on here? What's the goal? Draw a picture if possible. And so we're just trying to understand the situation rather than picking numbers, asking yourself, what equation do I need to get the answer, right? So we want to avoid that. We want to really understand what's going on, understand the situation. Don't just jump right into what you think is solving it, okay? What's the goal? Draw a picture if you can, all right? And then we've been emphasizing all semester quantities, right? What are the quantities involved? Distance, velocity, volume, weight, temperature, etc. What are the relevant quantities? Okay, we know that the relationship of quantities is what forms our functions, right? Relationship of quantities forms our functions. And then we want to ask which quantities are changing and which are constant. Which ones change together? So the quantities that are changing, we may assign what to those? Remember we talked about this in the beginning? Variables. And if quantities are constant and we need something to represent those, yeah, so if we, a parameter, right? And so maybe we have the value, so we don't need to assign a letter to it, but just that's the idea of a parameter, is a letter, which would be a quantity that stays constant, okay? And remember, so with optimization, what will the goal be? This is going back to number 1. The goal will be, with optimization, trying to maximize or minimize some quantity. And so then after you orient yourself to the problem, again, I'm going to hammer it again. The centerpiece of the solution will be the function whose dependent variable is the quantity to be maximized or minimized. Your whole solution will be about this function. The first half of the solution will be creating that function and finding the applicable domain. And then from there, now we're using that, and we're going to what? Find the critical values, find the endpoints, and then get our list of possibilities to see how we get either the greatest value of the dependent variable or the least. All right, so the thing about these problems is they're all different. They're all different, drawing on your last 6 or 8 years of math. Trig, velocity, time, and distance. I mean, they're all different, okay? And so I'm trying to give you something about them that's all the same, which is this idea that you're going to be building this function with applicable domain. That function's the dependent variable is the quantity that we want to maximize or minimize. And then we're going to analyze it by looking at the critical points and the endpoints of the applicable domain. So that will always be the same. But the orienting yourself to the problem and setting up that function, it's going to be different in every case because all the problems are different. There's no cookie cutter to this. So let's try one. Okay, so a rectangular storage space is to be created against the building using 84 feet of chain link fencing. Fencing will comprise 3 sides of the space, and the building's wall will form the 4th side. The space must not be narrower than 4 feet. What configuration of the storage space maximizes its area? So how do we want to start? We want to really understand, visualize what is going on. So we want to start with a picture for sure. Okay, we want to start with a picture for sure. So looking down from above, say this is the building here. Okay, and what is this storage space like? It's going to use 84 feet of fence, and the fence will comprise of 3 sides, and the building's wall will form the 4th side. So if you're reading that and imagining it correctly, you're thinking something like this. Where the blue is the chain link fence. The blue is the chain link fence. Okay, so the idea here is there's lots of different configurations of storage space that we could make. Right? That's not the only one. How else could I make it? So again, here's the building. Here's the building. How else could this thing look compared to that first one that I drew? All right, so he wants one that's skinnier, but like it extends further from the building. So it's not as wide. It's not as wide, but then it'll extend further from the building like this. Is that a possibility? Okay, what else? A square, good. So one that has the width and the distance out from the building is the same. And then one more. What's another extreme case that you could have here?
The one that's kind of
Okay, so it's really wide, but doesn't come out very far from the building. Okay, so here's 4 possibilities. How many possibilities are there? There's an infinite number. Okay, you can imagine starting kind of with this one, and you could imagine the two sides here kind of moving towards one another, kind of, so this width is narrowing, and then as that happens, this side would move further and further away from the building, right? So we'd have this first, and then this one, and then this one, and then this one. And then imagine even one like this. Not practical, but possible in this situation, right? So we've got all these different configurations. As we imagine that thing getting narrower, the side parallel to the building gets further away from the building. So then we should ask ourselves, now kind of getting a feel for the situation, what's changing and what's constant then? What's changing and what's constant? So if I just use this one as my generic, like we're going to consider this as all possibilities now. This one is just kind of representing all possibilities, although we know that's only one possible shape. What is varying? Yeah.
Varying is the length of each side, and staying the same as the total amount of fencing.
Okay, so this length is varying, and then as that length varies, this length varies, but the total amount of fencing stays the same. So we can use variables, right? So we could call this length, say, x, then this is also x, and as x changes, we said this changes too. Call it y. If you want to use length and width, whatever variables you want, I'll just stick with x and y, okay? All right, so given those variables that I chose, again, what's the goal? The goal, or the centerpiece of the solution, will be? But our solution, yeah, so we want to maximize the area, but what's the centerpiece of the solution to the problem? Where's Kamal? Is Kamal here? Is let's see, Alejandro here? Jans? There he is, Alejandro. What's going to be the centerpiece of the solution to this problem? Okay, good. So it's the function whose dependent variable is the quantity we want to maximize. What's the quantity we want to maximize? So right here is the key. Maximizes the area. So I want an area function, right? So I want my area, say, as a function of x is fine. All right, and so area is going to be a function of x, and what rule or formula is going to give me the area of this thing? X times y. But what's the problem with that? Two variables. Okay, so we got the general structure of our function, but we need to get rid of the y. If I want to do a function of x, I need to get rid of the y. So we're almost there. So how am I going to get rid of that y? So this is where this fact that all the feet, we got 84 feet of fence to work with. And so if we do x plus y plus x again, that needs to equal 84. And so y is 84 minus 2x. It's just a little side work, a little fact, right? Crucial, but much less of the focus than this. Our function is the focus, right? Our function is the focus. So we're going to take 84 minus 2x, since it's the same as y, and we can put it there. And now we've got our function definition, x times what? 84 minus 2x. What's left to finish the function? One more part to the function that we need. What's that? Right, applicable domain. So x Could be as small as what and as large as what, right? So what's the smallest that x could be?
4.
Good, right. It says that the space must not be narrower than 4 feet. So x would be 4. And then what's the greatest x could be? Well, that's when what?
40. It's when x is 40.
But how did you know that?
Because because I set y equal to 4.
Right, that's where we're going to begin. So if the narrowest it could be that way is when y equals 4. And so then that means what would x be? What's the greatest value of x when y is 4? So we've taken up 4 feet for y, so we got 80 left, but that 80 has to be divided into 2 sides. So I think he was right, 40. Got it. Half the problem is done. We got the function whose dependent variable maximizes the area, and we got its applicable domain. Questions on that? Notice how long it took us to really understand the situation, drawing several pictures, defining variables. Okay, now what? So we're going to do endpoints. What are the endpoints? 4 and 40. Critical values. F prime of x equals, let's not do product rule, let's multiply this out. It's 84x minus 2x squared. So we're going to get 84 minus 4x. Did I do the math right? For the derivative? 84 minus, yep, minus 4x. And so x is going to be 21 is a critical value. So now our possibilities are 4, 40, and 21. Endpoints and one critical value in the domain. We're going to plug them in and get f of 4, f of 40, f of 21. For time's sake, I know that f of 21 is going to give us the biggest value. And what will it give us? 21 times 84 minus 42. Is that 42? 21 times 42? Whatever that turns out to be. And what configuration gives us that maximum area of 882? X is 21, and Y is? You can figure it out, right? You can figure it out from, you got 21 on the left, 21 on the right, and what's left? 42. So X is 21. Y equals 42. Okay. Like I said, all of these are different. Every one you come to is drawing on all different things you've learned in your math career. So it's going to take time to work on these.